Question 1. Nuclear exchanges. Surface area of a sphere is 4 pi r squared. Distance from the Sun to the Earth. Hang on a tick. What is that? What to do with that? Nuclear exchanges. Well, the Sun is a giant nuclear site for fusion, so maybe that's got something to do with it, but what's the distance got? We'll see, and the speed of light is given as well. A. Nuclear fission, that is splitting atoms apart, and nuclear fusion, that is joining atoms together, are opposite processes, yet each releases energy. Explain why this is not a contradiction. Okay, a contradiction is something which is inconsistent or doesn't make sense. And you would think with opposite processes that one would perhaps give energy and the other would take energy, but that's not the case. Okay, to answer this and explain the apparent contradiction is because is to understand. I'll start that again. To explain why it's not a contradiction, you have to understand how fusion and fission work and how they the energy works, the release works. Binding energy, very important. Binding energy is the energy, if you put it in one way, it's the energy used to bind all the nucleons in a nucleus together. Okay, that's not strictly speaking correct. Put it another way, it's the energy that you have to give them to separate them from each other, so that all of those nucleons are pulled apart. Now, some atoms have a greater binding energy than others, which means it takes more energy to split them. However, you can make an energy gain if you go from one nucleus that has a lower binding energy to another nucleus which has a higher binding energy. So let me explain that. It sounds a little bit unusual. So you want to go from low binding energy, I'll call it Be, to something with high binding energy in order to have energy come out. Something with low binding energy means that there's not as much energy required to hold the nucleons together. Something with a high binding energy means there is more energy required to hold them together. However, that energy required to hold them together is energy that's been taken away from them. So they're able to release more energy as they go from a lower to a higher binding energy. And that energy that comes off is in the form of, well, it used to be mass. So these nucleons, as they were further apart, they all had a greater mass, but when you bring them close together and they bind with a strong nuclear force, they decrease in mass, and that drop in mass is given off as energy according to Einstein's E equals mc squared. So this idea of low binding energy to high binding energy is very important, and where the non-contradiction thing occurs is that the graph of binding energy per nucleon according to versus the number of nucleons. So as it gets heavier atoms going to the right, it doesn't go up and keep going up. It goes up and then goes down. It goes up. There's a little jump here, and it hits a peak, and then it starts coming down at a sort of a shallow steep. And this atom in the middle is iron. Iron is the most stable. It has the highest binding energy, which means the atom nucleus has the least amount of energy. So iron has converted the most amount of energy to mass. Fusion works, you might start with uranium and go that way, and you're decreasing the size of the nucleus. You might end up with krypton and barium, I think, is the usual products when you split a nucleus atom, and they have a higher binding energy, which means a lower mass, which means more energy has been converted to heat and light and whatever that you would use to power a nuclear power station or something like that. Okay, so it's not a contradiction, and the other way is your fission fusion, where you're joining atoms, fusing, that's fusion, together to increase the binding energy or the amount of energy that's given off. Okay, you should be able to get at all of that. B, explain why controlled nuclear fusion, that's joining atoms together, is difficult to achieve. Okay, fusion, first of all, you're getting, you might have a helium nucleus and another helium nucleus, and they're coming together, and they have to squish together to form a what's got, well, it could be a number of things with 8 nucleons, but usually you'd be dealing with beryllium, 4, is that right? Hydrogen, helium, lithium, beryllium, 4 protons. So in any case, that fusion, you have to you have to get them to first of all hit. Remember, atoms are really, really small, so it's hard to make the collisions. So is collisions 1L or 2? I don't know. You know what I'm writing anyway. So it's hard to make the collisions. If the collisions do occur, you've got the electrostatic repulsion, which is your positively charged nucleus from the protons, which are repelling each other. So you've got to have enough either pressure and heat to ensure those pressure and heat go together in most cases, in all cases. I have to double check that. And you with the heat, the kinetic theory of matter talks about the vibration. So they move and they're continually vibrating. The particles, with more heat, they vibrate more, and more vibration means you're more likely to get a successful collision. So you need a lot of heat. And remember, what holds a nucleus together, this comes into a later question I believe, is the strong nuclear force. So you have to get close enough for the strong nuclear force to take over so that they'll combine. The strong nuclear force works on a very, very tiny scale. The electrostatic repulsion works on a bit larger scale, so that that will work. The electrostatic repulsion, that is, will affect it more until you get it close enough for those nucleons to bind together. So that roughly covers it. Whereas fission, it's so much easier to split them apart, because all you have to do is provide, depending on how you do it, if it's radioactive nuclei, you can just leave it sitting there and it'll split apart by itself. Also, you can sometimes bombard them with neutrons, uranium with neutrons, to create an unstable nucleus, and that's a little bit easier for it to suck one neutron in, which is neutrally charged, so it doesn't have the electrostatic repulsion, and if you send enough of them in, you're more than likely for it to occur, and extra nucleon in there makes it more unstable. So anyway, hopefully you can see from that why fusion is difficult to achieve. It's just not as likely, so you have to have very, very specific conditions for it to occur. So specific conditions, whereas those conditions for fission are much easier to set up.